Okay, question number 3. Let us begin with this. Okay, question number 4. So this video will be published on, this is a problem for Thursday, which is on 12th December 2024. Okay, fine. A string of length 0.8 meters fixed at both ends. Now we are doing a problem on waves, and there's a string over here, which means what? So when you get this information saying that this length is 0.8 meters, the first thing that you need to infer is, what does this tell you? Okay, so to infer that, what we do is, let me draw this baseline. This will provide me a clue as what is it I am referring to. Now when I draw a baseline, what is that you conclude? See, this is one full wave here, this is one more half wave over here, which means what? The length of this segment from here to here, this would be lambda and this would be lambda by 2. So total length is 3 lambda by 2, right? So this is what I get. That's 3 lambda by 2, I can equate it to 0.8. So 3 lambda by 2 is equal to 0.8. Lambda should be equal to 2 into 0.8 divided by 3. When I do this, what is that I get? I get this as 2 into 0.8 divided by 3. I get 0.533. 0.53 meters. What is it now? This is your lambda wavelength. If lambda is been given and if velocity is given, you can find out the frequency, right? That's where I'm looking into it. Okay. Now the variation with time t of the displacement of the particle p is shown. Okay. So therefore, now you look at the amplitude here. This amplitude appears to be, let us say for example, A here. This is the maximum peak point over here. If you look at this point over here, this should be A. And if I draw a horizontal here, look at this. This appears to be nearly mid of it, right? So what I will do is, I will consider this height, the position of Q with respect to the baseline, as A by 2. Physics is full of assumptions, so we should always start with assumptions, right? A by 2. The variation what time t is known. Okay, draw on the axis a graph to show the variation t of the displacement of the particle Q. Displacement of the particle Q. Now what is it given? It gives you, this graph gives you the displacement of the particle p. Okay, displacement of the particle p. Now what is that being given here? At t equal to 0, it says p is at this point. Is it real? See, don't compare this graph with this graph. Okay, this is just a profile given here and p is a particle here. So do not say, hey, here it should be 0, but here also it should be 0, but unfortunately here it is larger. What does it mean? Don't compare with this. Okay, so what you need to do is, at t equal to 0, the p's amplitude is equal to so much, 2 units. 2 units is the amplitude just given over here. Now let us look at this. At t equal to 0, it is something like, if I take this one here, okay, I take a snapshot of, when the wave is going like this, I take a snapshot of it. I take a camera, I take a snapshot of it. I observe this is the amplitude. Okay, so therefore that is what is being shown here. See this, if I consider this as 2 units, this is also 2 units. At t equal to 0, p was here. At t equal to 0.2 seconds, what would have happened? The wave would have gone here. This could have been the wave. This could have been the wave here, right? So that means, where is the point P now? The point P is at this point over here, which means the amplitude of P has reduced. See, I'm just going to, because this is nothing but the point here, right? So this point would be here. So as a result of it, P is reduced. At t equal to 0.4, where is the wave here? At t equal to 0.4, this could have been the wave over here. This could have been the wave. So as a result of it, sorry, this could have been the wave. This could have been the wave. Okay, so therefore, where is P here? P would have come here. P would have reduced. Okay, and then at t equal to 0.6, 0.4, 0.6, 0.7. At 0.7, wave would have started from here. So this would have gone like this over here, which means the amplitude of P is 0 over here. That means the amplitude of P is reducing. Amplitude of P is reducing. That's what has been shown. Okay, now let us look at Q here. Now what is happening to Q? When I took the picture of P, what was the value of Q? The value of Q was A by 2, right? The amplitude of Q was A by 2. So therefore, the amplitude of Q, was it plus A by 2 or minus A by 2? Minus A by 2. It is something like me and my brother both are standing at one location. Okay, you have a camera with you, you take a picture of me. Now what do you see? I stand at this much height and my brother stands this much height. So as a result of it, what is the amplitude of my brother? What is the height of my brother? This is the height, right? So you are going to picturize the height of the Q, which should be half of it. Why half? Because here if it is 2, this should be half. Why half? Once again, because we already picturized this as, if this is A, this should be A by 2. We took it across. So thus, so my Q will start from here. Q will start from here. This will take some time. It will not end in 11 minutes. Take some more time also. Okay. And then, now what is happening? When Now whatever is the sequence of events happening to this, the same sequence of events happens to this also. Okay, now as a result of it, now how does the graph goes like, now when this achieves something like, now P keeps on coming downwards, and after one full cycle, now what do we see, at Q is half of the amplitude. Okay, and now let us say P starts from here, and once again P reaches this point. P reaches this point. Okay, here, okay, we have the amplitude here itself. When P reaches this point 0, where does the Q reach? Q will also reach this point. Why should it reach that point? If you ask me this question, now see, as it comes down over here and reaches the position 0, when the amplitude of P becomes 0, the amplitude of Q also becomes 0. What is the reason? If you ask me this, the reason is because we are having a stationary wave here. Okay, when the particles, when if I have a particle here, particle here, particle here, we have all particles. All these particles jump together. All these particles jump together, right? Okay, I have one particle here, second particle here, third particle. All of them jump together. But only thing is, one of these particles is privileged enough to go to a larger height. The other particles do not have that privilege, right? Some of them will jump only to a smaller height. Some of them will be at 0 position. So this is what is happening in this segment. In this segment, all the particles are going to the downwards. Now, when this particle comes to this mean position, the particles here will also come to the mean position, because it's a stationary wave. I hope you are understanding what you mean by stationary wave. In a stationary wave, every particle that is present here will jump equally, and the particles which are adjacent to the next node will jump equally downwards. When this comes upwards, this also will come downwards over here, right? So it happens like this. It swings like this. It goes upwards, it comes down like this. So it goes upwards, this goes downwards, and then it comes downwards, and both of them are equal. So this is how it happens. So therefore, when all the particles are going upwards here, all the particles here are going downwards. Okay, when these particles come upwards, these particles come downwards, and all of them are in the same line. So therefore, when P comes downwards, Q should go upwards, so that when P becomes 0, Q is also 0, right? And hence the instantaneous amplitude becomes 0 over here. Now it is 0 here. Now once again, when P reaches this point, that means P has reached its maximum. Then where does Q reach? Q reaches this point, right? Q reaches this point. When P reaches 0, then what is, so it is what? P has reached, this is my central line. P was initially here, P went downwards here. So this is like this. P is here, then Q is here. When P went downwards, Q went upwards, right? This is at 0.7 here. Sorry, at 1.2 or 1.4 here. Okay, Q is at 1.4 now. Okay, and after that what happens? When Q comes downwards, P is at the center. Okay, and then when it comes downwards completely, this goes, sorry, when it comes downwards, P goes upwards completely, which means, so this goes upwards over here. Now, so I should be getting like this. And once again, the same sequence of events will continue. So this is the graph that we should get. Okay, right. So this is your Q. Then, if you do not understand, do ask me. Maybe I will try to do an experiment and show you how does things change. Maybe I'll write a code in GeoGebra or something like this, or I'll take your help and then do it as well. Right, and then, so we have drawn the graph. How much marks is this graph? 2 marks. Wow. Calculate the speed of the waves on the string. Okay, now T is in milliseconds. Now, if you want to calculate the speed, what do we need? We need V equal to F lambda, right? Is a lambda known? Lambda is known earlier. Where did we know? We got the lambda from here, right? Lambda is known. That's what I asked you. To find out the value of lambda, it will be kept handy. Now I need to get the value of F. How do I get the value of F? See, starting from this point to this point, from this point to this point, what is this now? This is one time period, peak to peak, right? So your time period is equal to 2.8 unit milliseconds. So frequency should be 1 by 2.8 millisecond. Let us calculate what is that value. So which comes out to be 1 divided by 2.8 should be 0.3571. So I will write this as frequency is equal to 0.3571 into 10 cube, which should now be equal to 357 hertz, right? And but I need velocity. So how do I calculate velocity? Velocity should be 357 multiplied by, what was the lambda value? 0.53. 0.53. When I do this, what is the answer I get? I get 357 star 0.53. I get the answer 189.2, which is nearly 190 hertz. Sorry, not hertz, 190 meter per second. So I got the speed of the waves on the string. Okay, 4 marks out of 10. We have done only for 4 marks, and that too 10 minutes almost done. Okay. It is suggested that the speed c of the waves in a string is related to tension force T in the string according to the equation T equal to AC square. Determine the fundamental SI unit for A. Very simple question. T equal to AC square. T equal to AC square. A should be equal to T divided by C square. What is T? T is tension. What is tension? Force, which should be Newton. What is C square? Meter per second, velocity, right? Meter per second the whole square. I'll write Newton as kg meter per second square, and this will be meter square per second square. Second square goes off, square and meter goes off. So you should be getting kg per meter, right? So kg per meter, and thus the unit for SI unit, fundamental SI unit is kg per meter. Okay, and then the tension force on the string is doubled. Tension force on the string is doubled, becomes 2T. 2T. Describe the effect, if any, on the change on the frequency of the standing wave. Now, what is being given for the formula? T is equal to AC square. So T dash should be equal to, A is a constant, it doesn't change. Now what is happening? C should change over here, right? C dash square over here. Let us divide one by the other. T dash by T is equal to AC dash square divided by AC square. A goes away. So I will have, what is T dash? T dash is double the time, right? So this should be 2T divided by T is equal to C dash by C, the whole square. Now this T cancels away, you get 2 here. Thus I have C dash by C is equal to root 2, C dash is equal to root 2 times C, right? So C dash is equal to root 2 times C. What is being asked? Frequency. What happens to frequency? Now we know that C is equal to F lambda, right? So therefore I can now write F dash into lambda should be equal to root 2 times F into lambda. Lambda doesn't change because you're getting the same 3 loops. Length is same. Lambda doesn't change. So lambda goes away. So F dash will be equal to root 2 times F. Okay. Thus the frequency increases by root 2 times the original frequency. Okay. Next. The standing wave on the string creates a traveling wave in the surrounding ear. Okay, so it is like a guitar string. Okay, so it starts vibrating like this, and as a result of it, it creates a sound. Outline one difference between a standing wave and traveling wave. Yesterday in the class also we saw this standing wave. What does standing wave do? Standing wave traps the energy. Right? Traps the energy. Traveling, what does it do? It transfers the energy. You can write this. The other example, difference between them is that in a standing wave you get nodes and antinodes. In case of a traveling wave you get a crest and a trough. You can mention this also. Okay, we need only one point, any one of them is fine. Then the sound wave is an incident on the surface of water. The wave makes an angle of 30 degrees with the normal to the surface. It's incident here, normal is here, 30 degrees is here. The speed of sound in air is 340 meters per second. This is V here. Water, it is 1500 meters per second. Which means what? This is 340. This is 1500. This speed is larger than this one. Which means what? This is your rarer medium and this is your denser medium. How do you classify rarer and denser? When the speed of the signal is higher, that is called as a rarer medium, and when the speed of the signal is lower, that is called as a denser medium. Okay, so in case of light, air becomes a rarer medium and water becomes a denser medium, and here it is a ulta, it is the opposite of it, right? Now discuss whether the sound wave can enter the water. Why shouldn't it enter the water? Let us understand that. Okay, now what does it mean? Now this ray is going from a denser to rarer. Whenever the ray goes from denser to rarer, we have one problem. What is that? That is nothing but the ray can get internally reflected like this. When can it get internally reflected? If the angle of incidence theta is larger than the critical angle. Which means what? This is incident angle theta. So theta is equal to 30 degrees here. Is this larger than the critical angle or lower than the critical angle? If you are able to understand that, then automatically your problem is solved. So how do you find out what is the critical angle? You should find the critical angle here, right? If you get critical angle to be 35, then definitely you can say, hey, water goes inside the, sorry, the ray goes inside the water. If it is less than 30 degrees, let us say your critical angle is some 15 degree, then what can I say? No, the ray does not go inside the water, it gets reflected back, right? So you need to get the value of the critical angle. How do you get this? Though we know the formula of a critical angle is mu sine C is equal to 1. This is what we applied in light waves. We can apply this also this in sound waves. What is mu here? Mu here is nothing but the refractive index of the denser medium. Okay, I do not know what is that value. Let us calculate this. If I want to know this, I want to get this value here. See, I want to get this value here. I need to get the value of mu here. So what I will do is, let us find out what's the value of mu. What is mu given by C divided by V? What is C? Refractive index of the, sorry, the velocity of the signal in rarer medium, and V is velocity of the signal in denser medium. What is the velocity of the signal in rarer medium? 1500. What is V here? V is 340. So I cancel this. You get 150 by 34. Let us calculate what is 150 by 34. 150 divided by 34 will be 4.41. Wow, it's very, very high. Okay, so value of mu is 4.41. Now let me substitute here. I get 4.41 sine C is equal to 1. Sine C is equal to 1 divided by 4.41. When I do this, what is that I get? Let me calculate that also. Let me take the reciprocal. 1 divided by 4.41 is equal to 0.2267. Is equal to 0.2267. So what's the value of C then? C is equal to sine inverse of 0.2267. When I do this, what's the angle? I want to get the angle. So what I will do is, I will retain this like this, and I will go to trigonometry. I'll go to second, and I will click on sine inverse. When I do this, sine inverse of 0.2267 is equal to, what is this I'm getting? No, I made a mistake. Just a minute. I'll just cancel this. I'll write it once again, 0.2267, and I will raise second, and I will go for sine inverse. Go to sine inverse, go to second here, sine inverse of this. I get 13.1 degree. So I get this answer as 13.1 degree. Now what is the value of theta? Theta value is 30 degree. So this is 30 degree, and this is 13.1 degree. So what's happening? This is lesser than this. So your angle of incidence is less than C, which means what? The ray will not enter the water. It will get reflected, right? So it will undergo a TIR. It will undergo a TIR because it's greater than the, critical angle is 13.1. I am sorry, this is greater than, not less than. Okay, critical angle is 13.1, but you are making this ray of light to incident at 30 degrees. So definitely this will not move into, and as a result of it, it will get reflected back. So thus you get a TIR. So wave will not enter the water. This is the answer for it. So you should say discuss. So discuss for 2 marks. You need to write the whole thing, and you say hence the wave will not enter the water. Enter the water surface. Enter the water surface, right? I think we have come to the end. Thank you. Do subscribe to my channel for more updates. Thank you.